In this tutorial, we will show how to use the SAP 2000 nonlinear shell element to model concrete shear walls. We will model a single planar wall, 10 stories tall by 20 feet long. The wall is 12 inches thick. It will be subjected to both a dynamic time history analysis and a pushover analysis. With an aspect ratio of more than 4:1, we are primarily concerned with the nonlinear behavior in flexure and will assume shear deformation to be elastic. Story-to-story height is 9 feet 3 inches, and the wall has a tributary area of 3,000 square feet. The floors are 6-inch slabs, modeled as rigid diaphragms, and all concrete is 4,000 psi. Three different levels of reinforcing exist in the model. Walls with a reinforcing ratio of 0.3% exist in the upper 6 floors in unconfined concrete. Walls with 0.4% reinforcing in unconfined concrete exist in the lower 4 stories. And boundary elements 4 feet wide with 3% reinforcing and confined concrete exist along the outside of the bottom 4 floors. Now we will put the model together. First, we look at the materials. There are 3 material types that we will use in this model. All steel reinforcement for the rebar, confined concrete for the boundary elements, and unconfined concrete for the remainder of the wall. Select the all steel reinforcement. The Show Advanced Properties box should be checked so that we can view the nonlinear behavior. This is the rebar material, and it is uniaxial. This is important when we assign the material. Note that the weights and masses are set to 0. All loads and masses will be done as assigned point loads. Note the stress limits and click the Nonlinear Material button, and then the Show Stress Strain Plot button. Next, we go to the confined concrete material. Note that it is isotropic. Again, the weights and masses are 0. The compressive strength is set to 4 KSI. Going to the nonlinear material data, we can view the stress strain plot. Note, as we move along the plot, the material carries no tension. Last is the unconfined concrete. Again, 4 KSI compressive strength. But this material is marked by a sudden degradation in load carrying capability post-yield. Next, we will define the area sections that represent our 3 different wall sections. We will start with the lightest reinforced section, the section with a reinforcing ratio of 0.3% and unconfined concrete, and we will use the layered nonlinear shell. This is the key to modeling nonlinear behavior of walls, as it allows us to define different layers for concrete and reinforcing. The layer definition data area is where we describe each layer in detail. The layer name, the thickness, the type, the material angle, and the behavior in the different component directions. We could enter the properties for each layer directly, but for this model, we are going to use the Quick Start option instead. For this section, our concrete material is the unconfined concrete with the all-steel reinforcement. Our thickness is 12 inches with reinforcement in 2 layers. We want the in-plane behavior to be nonlinear in the vertical or 2-2 direction for flexure. Out-of-plane behavior will be kept linear. For this wall section, we want a reinforcing ratio of 0.3%, and 2 layers of number 4 bars at 12 inches on center gives us a ratio very close to this. We can now see that our layer definition data form has been fully populated. We will now edit the form to simplify our model. The first layer represents our concrete membrane behavior. It is 12 inches thick, uses unconfined concrete, and is nonlinear in the vertical 2 direction. It stays as is. The next layer represents reinforcing in the horizontal direction. Since we anticipate shear behavior to be elastic, we will delete this layer. The next layer represents our first layer of vertical reinforcing. Again, membrane behavior using the steel material. Note that the material angle is set to 90 degrees in order to get the material rotated in the vertical direction. The steel material is uniaxial with properties defined in the one direction. Note that this layer is also nonlinear. We will delete the next layer as this represents another layer of horizontal reinforcing. And it is followed by the second layer of vertical reinforcing, which remains. The next layer represents the out-of-plane behavior of the concrete. We are going to reduce the thickness to 7.5 inches, which reduces the out-of-plane stiffness by 75% to include the effects of cracking. This is not really necessary in this model, but in a 3-dimensional model with flange walls, this reduction would limit the out-of-plane load carried by the transverse walls. The next 4 layers represent reinforcing in each direction, top and bottom, for the out-of-plane behavior. We will remove these layers for this model. We are left with a total of 4 layers: concrete membrane, 2 steel layers oriented vertically, and a concrete plate layer. These layers are illustrated in the graphic display. Now that we have our first section defined, we will copy it to create our other sections. Our next section will have a reinforcing ratio of 0.4%. For this section, the concrete membrane layer remains the same, 12 inches thick, with unconfined concrete and nonlinear behavior in the vertical direction. All that changes in this section is the amount of reinforcing. Each layer will be 0.02583 inches thick, which corresponds to number 5 bars at 12 inches on center. The two layers combined give a reinforcing ratio of approximately 0.4%. No changes will be made to the layer modeling the concrete plate behavior. The last section to be defined will be for the boundary elements. This section will have a reinforcing ratio of 3% with confined concrete. For the concrete membrane layer, we need to switch the material type to confined concrete. The reinforcing in each layer is increased to 0.1667 inches thick, which corresponds to number 9 bars at 6 inches on center. The two layers combined give a reinforcing ratio of approximately 3%. We will also switch the material for the concrete plate layer to confined concrete. Now we can draw the wall. Click the Quick Draw Area Object button and select the 3% confined section. These are the boundary elements in the bottom 4 floors. Next, switch to the 0.4% unconfined. This is the wall in between the boundary elements. Last, select the 0.3% unconfined to draw the remainder of the wall. Leave the draw mode. Select the bottom joints and assign restraints. Next, we will add rigid diaphragms at each level. Select the joints and go to the Assign Joint Constraints command. Select Diaphragm and the Z-axis constraint. Check the Assign a different diaphragm to each level checkbox. We can see that the program has defined a separate diaphragm at each level by going to the Define Joint Constraints command. Next, we will define our loads. We have 2 load patterns, dead and live. The dead load consists of a 6-inch slab, walls, and partitions and cladding for a total of 105 pounds per square foot. The live load is 50 pounds per square foot. We will include 25% of the live load in the seismic analysis. The same loads will be used for both floors and roof. At the beginning of the tutorial, we said that each level supports 3,000 square feet of tributary area. The loads will be broken up as follows to each of the 4 joints at each level. The 2 exterior joints support 1,000 square feet of tributary area with a resultant dead load of 105 kips and a live load of 50 kips. The 2 interior joints each support 500 square feet with a dead load of 52.5 kips and a live load of 25 kips. Select the exterior joints and assign the dead load of 105 kips. And then the live load of 50 kips. Select the interior joints and assign the dead load of 52.5 kips and the live load of 25 kips. We have also defined an earthquake function. This record has a peak spectral acceleration of 0.425 g. We will scale it up to 1.5 g when we apply it to the model. Because we are doing a dynamic analysis, we need to instruct the program on how to calculate the masses. Here, we will calculate the mass from the applied joint loads. And as stated earlier, we will include a quarter of the live load. Now, we will review our load cases. We have 4 cases. First is modal. It is always a good idea to take a look at the modes to verify the model. Our next case is a nonlinear case for gravity loads. This case will be used as the starting point for the other load cases. In addition to the dead, we will include 25% of the live load. Our next case is for pushover. Again, this is a nonlinear static case. And note that the gravity case sets the initial conditions. A check of the load application shows that we are using displacement control out to a magnitude of 44 inches in the y or x direction, and we will use joint 32, which is at the top of the model. The last case is for the time history. Again, it is nonlinear using direct integration, starting from the gravity case. We are applying the previously reviewed Motion 1 record with a scale factor of 1363. which both scales up the record and converts it from gravity units to inches. We are asking for 750 time steps at a time of 0.02 for a total of 15 seconds. Now we are just about ready to run the analysis. However, before we do, we will set the analysis to be a planar model, as we do not want to include any out-of-plane behavior. Now we can run the model. This may take some time as the program is performing 3 different nonlinear analyses, including a time history analysis. With the analysis complete, we can take a look at the results. A quick look at the mode shapes shows the anticipated patterns. For the time history analysis, we wish to look at the drift at the roof, or joint 32. We can do this by using the generalized displacements. We want the U1, or horizontal displacement, to be divided by the height of the building, which is 1,110 inches. On the deformed shape, joint 32 is located here. Next, we go to the Display Show Plot Functions command. Select the time history case and click the Define Plot Functions button. We are going to add the generalized displacement just defined, drift roof. We are going to plot the drift at the roof versus time. From this trace, we can see that the maximum drift is approximately 0.6%. Next, we would like to plot the strain in the boundary element at the bottom story. We will use the vertical displacements from joint 7 and go back to the generalized displacements. This time, instead of displacements in the U1 direction, we want displacements in the vertical, or U3 direction. We want the U3 displacement divided by the length of the story, 111 inches. We go back to the Show Plot Functions, and still using the time history case, remove the drift roof function and define a new function using the strain generalized displacement. Again, we plot against time. From the plot, we can see that the maximum strain is approximately 0.3%. The last item that we will plot for the time history will be a hysteresis loop created by comparing the rotation at the bottom story to the moment. To calculate the rotation, we will again use generalized displacements. We will again use joint 7, but divide the vertical displacement by the length of the wall, 240 inches. We will also use joint 18, which is at the other end of the wall, but with a negative scale factor. Now we need to create a section cut for determining the moment. Select the bottom story wall objects and the joints just above, and assign them to a group. Next, go to the Define Section Cuts command and add a section cut using the just defined group. Now we can go back to the Show Plot Functions command. We will add 2 additional functions. One for the rotation, and one for the moment. We will plot the section cut moment in the vertical against the rotation on the horizontal. This displays a hysteresis plot. In addition to the time history analysis, we also asked SAP 2000 to perform a pushover. We can plot the pushover deformed shape, or plot the stresses in the wall. Here, for step 1, we will plot shell layer stresses. We can plot by section type and layer name, or just by layer name. We will select the concrete membrane layer and the S22 or vertical component. Note how the concrete stress goes to 0 in the tensile region. We can also plot the stresses in the steel layers. Note how both tension and compression stresses exist. Lastly, we can plot the pushover curve. Here we display the base shear versus the displacement at the roof. This completes this tutorial on the modeling of shear walls using the nonlinear shell element.